The first speaker has many achievements. Among them, he is a recipient of the Sackler Prize. So Andre Bernevig from Princeton. So just wear this.
Okay. Cool. Thanks. Is there like a PowerPoint? Is there like a laser?
Is it possible to use the mouse as a pointing device? Because we are
Not particularly. Just maybe like some stick.
recording the screen.
Yeah, but I can't use the mouse as if like it just doesn't.
Right. I think
I mean,
very much that the recording you can.
you're not recording. You're recording through the.
Yeah, we are taking the test to capture the destiny. Try. If no, do whatever you
Because I can't. Well, they want me to use the mouse as a pointer, which is not.
تاخد المستيك طيب تاخد نوت إجابة سيلو.
מה לא רואים?
לא, אל תחשב.
לא נחשב.
Okay, so hello. Thank you for coming here. This is going to be. I'm going to have to use, because it's going through the audio system, apparently the pointer as the mouse as a pointer. I'll probably get annoyed with this in the first two slides and not do this. But today I want to talk about topological states of matter. And since I'm the first, since we go alphabetically, apparently I'm the person that has to introduce a lot of concepts. So probably all of you condensed matter physicists are going to get bored in today's talk, at least in mine. But hopefully I'll try to spice it up at the end. So before I start, I wanted to thank a bunch of people. And there's a bunch of my students, postdocs, and collaborators that I've worked with over the years. But basically, I want to thank the people that without whose work I wouldn't have been able to get this prize. My advisor, Su Sheng Zhang, in grad school, my postdoc advisor, Duncan, and my good friend and collaborator, Taylor Hughes. I also wanted to thank the other two recipients of the prize for, keeping up such a competitive environment and always having to look behind my shoulder as they're passing me by in this field. So thank you, Liang and Xiao Liang, for everything. I also want to thank everyone. If you've known me, you know I come here a lot. That's because I have a lot of friends here. And, I think they're friends. They probably think I'm just an annoying relative showing up at their doorstep every once in a while. So thank you all the people that I know here. And not least, thanks to the Raymond and Beverly Sackley International Prize for doing this every year and for keeping science interesting with these young prizes for young scientists. So, as not all of you are condensed matter physicists, I actually don't know what the proportion is, but as all of, and as this is a colloquium style, let me tell you a little bit about what we do as condensed matter physicists. So our purpose in condensed matter physics is basically to find out new states of matter, to look at systems and try to understand what they're made of and what they can achieve. So this talk will be about several new concepts and several new states of matter and the physics they kind of unraveled. So I'll talk about topological insulators with and without symmetries. Then I'll try to, towards the end, talk about topological metals and new fractionalized states of matter, fractional topological insulators. So as I said, we're trying to, condensed matter physicists, trying to understand what the world is made out of and what states of matter it can make, it can have. And this is kind of a concept that started off in ancient Greece and and moved on over the centuries. But basically, it turns out that our ancestors, despite their limited knowledge, kind of had the right idea. So the idea that they had, and this is the idea that's kind of lasted from Aristotle to Newton to beyond, is that you've got the same constituent forces, and although they were finding out that you've got gas, liquid, and solid states of matter, the incipient physics that of course was available with the experimental methods at the time, they kind of realized that basically all these states of matter are given by same constituent forces in different environments. And this is really an idea that kind of progressed in the 20th century. So everything that I'm going to be talking about and everything that we do in condensed matter basically has to do with electrons and atoms, for example, in cold atom physics. But the ingredients of the matter are basically all the same, and the question is what kind of states of matter it can develop. So we saw the classical states of matter, the liquid, the vapors, liquid, and solid. But the 20th century kind of brought about a new revolution in condensed matter. So there was the time when experimental techniques could really power up and find the states of matter, and theoretical techniques soon followed. It was usually the case that the experiment went first. And the 20th century saw a myriad of states of matter, and with it saw a classification of the states of matter by the concept of broken symmetry and appearance of an order parameter. So for example, the simplest example that everybody can relate to is a magnet, and the magnet has a broken spin rotational symmetry. So you cool it down at high temperature, it's got spin rotational symmetry, you cool it down, and it picks a preferential axis that denotes, so it basically chooses a north and south pole. It's got a broken symmetry. And this order parameter kind of describes the state, and is the same basically for other states such as ferromagnets, ferroelectrics, antiferromagnets, etc. But basically, the main idea is that it's a local order parameter. So what do we mean by that? What we mean by that is that if you cut the magnet in two, you basically create a new north and a south pole. So if you're able to kind of zoom in into the magnet, you get kind of more information in the sense that you see that the spins are aligned in one specific direction. So that's a local order parameter. So I guess some people call it 21st century physics that spilled in the 20th century because it really got discovered in the 1980s. But basically people started realizing more and more that the same constituents such as electrons can give rise to other states of matter, and these states of matter are called topological phases of matter, and I call them topological just to distinguish them from the concept of broken symmetry order parameter. So in these states, the more you zoom in, the less information you get. They look like they have no local order parameter, so you have to zoom out to see what you get. So basically, this is kind of a picture that condensed matter physicists laugh at because it's kind of a stereotype picture in the field. But whenever I want to find out the concept, I just go to Wikipedia. And before I define topological states of matter, we should know what topology is. And topology is basically the area of mathematics that deals with the properties of manifolds that are kind of invariant or smooth under continuous or smooth deformations. So for example, all the manifolds drawn on this page are not smoothly continuable to one another. So for example, I have to drill holes, which is not a smooth deformation. So what does this have to do with physics really? Well, these manifolds are the manifolds on which we're going to define Hilbert spaces of quantum mechanical problems. So I told you what topology is roughly, so now I'll tell you what topologically ordered phases of matter are, or like what we're going to talk about. And I can't really give an overarching definition, but I can tell you several properties. So most of them are bulk insulators, so they have an energy gap. They have gapped ground states, and they're, at least in some sectors, and they're characterized by some sort of topological number. The full classification is not known of these states. Even in 2 dimensions, we don't know how to classify everything. And in higher dimensions, the situation is even more severe. But I can tell you several remarkable things that happen. So for example, interacting topological states of matter, which I'm not going to talk about very much until the end, kind of they feel the topology or the genus of the manifold on which they sit. So what do I mean by this? What I mean is that if you have a Hamiltonian that has as a ground state some topological state of matter, and it's an interacting Hamiltonian, it's a strongly interacting Hamiltonian that's got sort of fractionalized interesting excitations, this Hamiltonian is going to get different degeneracies of the ground state. This ground state and excitation spectrum is going to have different degeneracies whether you put it on the sphere, on the punctured disk, or on the torus. Okay? So that's very, very strange because none of these manifolds differ if you zoom in very closely. They just differ on a global scale. So that's how the Hamiltonian, the matter, knows about the topology of the space. It just has different degeneracies. You solve the matrix Hamiltonian, you get different ground state degeneracies if you're on the sphere or on the puncture disk. The non-interacting states of matter are even simpler in a way, but because they're simpler, they're much easier to deal with. And the non-interacting topological states of matter that I'll be talking about are band insulators. So since they're band insulators, all you have to do to get the ground states is fill some band. And if you fill some band, you're going to have no ground state degeneracy. So the ground states are the singly degenerate ground states, but they're topologically non-trivial in the sense that I'll define very soon. And that sense is that they cannot be adiabatically continuable to the atomic limit. And by adiabaticity, which is a concept I'll use all through the talk, I just mean that an adiabatic continuum is a change in parameter of the Hamiltonian that does not collapse the gap of the system. So these non-interacting states of matter, which is the reason for these prizes, are band insulators. And even though band insulators have been known for a while, these new states of matter discovered in the past 80 years were missed kind of by decades of band theory, which is very surprising. So let's start with defining topological insulators. And first let's start by finding trivial insulators. So these are two examples of trivial insulators. Turns out they're very, very useful, but from a physicist perspective, they're not very, I mean, you'd never do physics in kind of somewhere here. You try to stay away from it. But they're usually used for, you know, I guess one of the best insulators is fused quartz silica, which is produced in those type of situations. So that's kind of not that interesting. So what we want to do is find out something more interesting. So I'm going to define, so why are topological insulators interesting? Why are insulators that are not the ones that I showed before interesting? Well, the reason why they're interesting and the reason why we define them as topological is that most of them, and I'll come back to this, have gapless edge states when you put them in contact with trivial insulator. So let me just show you by definition how that's done. So I define the topological insulator as an insulator that is not adiabatically continuable to a trivial insulator. So I have to define what a trivial insulator is. So I'm going to do it now. So pick a lattice, for example, and make the lattice size, the lattice constant, the size of the Milky Way galaxy. If you do that, then all the hopping between sites will be 0, because they're exponentially small in the size of the galaxy. So, and now you want to build an insulator, because we're talking about insulators. So if I don't want a double unit cell, I'm just going to pick 2 orbitals per unit cell. So pick an S and P orbital, and this is a recurring theme that I'll come back to through this talk. You pick an S and P orbital, and if the energy of the S orbital is not the same as the energy, on-site energy of the P orbital, the system is an insulator at half filling. You just fill whichever orbital on each site, whichever orbital has got the lower energy. So far, no spin in the problem. Just think of spinless electrons. And this is the atomic limit. It's the most boring thing you can have because the wave functions don't have any momentum dependence. They're just kind of constants, and nothing interesting can happen. You just have an on-site energy. So now what you do is you perform this thought experiment. You say, well, I have this trivial insulator, and I've got my insulator in the laboratory. And I'm going to ask if this insulator that I have in the laboratory is it trivial or not. And there's one experiment that you can perform if you had infinite time. You could try to adiabatically continue this trivial insulator, the atomic limit, to your insulator in the laboratory by just, you know, taking the lattice constant and making it the size of angstroms from the size of Andromeda galaxy or whatever, or like doing some other path, any path. So if there's no path that you can take to make the lattice size of this insulator the same as the one in your laboratory, if there's no path that you can do that without closing the gap, then the insulator that you're left with, the insulator that you have in the laboratory, is topological. So that's kind of a definition that doesn't care about edge states, etc. So by any path you take, if you can't adiabatically continue this atomic limit insulator to your insulator, so there's got to be a phase transition, then the insulator that you're left with, that you've got in the laboratory, is non-trivial. As a result, just from this definition, if I have a non-trivial insulator and I put it close to an atomic limit, like here, then I'm basically going to get a region of gapless edge modes. And why? Why is that? Well, I can just make this distance very, very large, just like the sizes of, you know, 2 galaxies, make it huge insulators. And then basically my distance in between the two insulators is kind of the adiabatic parameter. So if I can't adiabatically continue between this non-trivial insulator and the atomic limit, by definition, this non-trivial insulator and the atomic limit, by definition, by what I said, there's got to be a phase transition, because failure of adiabaticity means a phase transition. So by definition, there's got to be some sort of a gapless edge modes. If I would now put more atomic insulator in this atomic limit insulator in this region, I would just move the gapless region. So that's kind of very important in the sense that the gapless region cannot be weeded out by disorder. I could disorder something, make it trivial. I could, just take, burn and vaporize, or just smash this part of the insulator here, make it trivial, of the non-trivial insulator, make it trivial, but the gapless region would just move here. So the gapless edge states are protected. And this is kind of just I basically haven't used anything but definitions. So now let me tell you how you get one of these. So the the hydrogen atom of the topological insulators is the quantum Hall effect. And this is where physics, 21st century physics, kind of spilled over in the 20th century. And this is kind of the hydrogen atom is the fundamental block. So what you see is there was a series of talks in the morning, so every condensed matter physicist is familiar with this, not only from talks in the morning, but for non-condensed matter physicists, what you do is you grab a sample of electrons and you put a magnetic field on the sample. And what you observe the following graph here. You observe the graph where you've got a Hall conductance that takes these steps. Well, this is Hall resistance, so the Hall conductance you can kind of see here. There is 1, 2, it's 1 over this one, 1, 2, 3, etc. So it's got these nice steps. So, and you see that the value of the Hall conductance, is just the Hall conductance is the coefficient of the X current to the Y field, and is just quantized in units of E squared over H. And you find out that if you do the experiment, this quantization is better than 10 to the minus 9. I actually think these days it's probably even better than this. There's experts in the audience that can confirm. So first of all, if I find something that's quantized, that's very interesting. Why? Because I know it's kind of stable. If I make a gap system and I find an integer number that characterizes this gap system, and by the way, this is the gap system because the magnetic field creates lambda levels. So if I find an integer, that's very interesting, because if I smoothly deform something, I can't change an integer smoothly. So if I have integers are kind of protected. The set of integer numbers is kind of protected under smooth deformations. So let's understand this insulator better. So I've told you that it's got a Hall conductance, so it carries some current, and this Hall conductance is quantized, and I haven't told you why, but I showed you the experiment. So now let's understand why. So if you look at the magnetic field, everybody knows that the magnetic field creates electrons localized in orbits that kind of run around in circles if magnetic field is strong enough, and these are basically the electron orbits in the lambda level. Now that means that the electrons in the bulk are localized and don't carry energy. However, on the edge, you can see that there's a problem on the edge of the sample, that there's no way to basically to have a localized orbit, because the orbit will hit the edge and will just bounce around and around and around. And that creates a motion in one direction on one edge and the other direction in the other edge. It creates these two edge states. So the system is a bulk insulator, but as I told you that it has a current in the previous slide, you should have immediately asked how can an insulator carry any current, because it's got a bulk gap. Well, yes, it's a bulk insulator, but it's an edge metal. So the moment you put edges on the system, the moment where you don't solve the system with periodic boundary conditions, which in experiments you always do, you have edges on your system. The moment you don't solve your system with periodic boundary conditions, you get these edge states which are metallic, which basically just flow in one direction on one edge, and in the other direction the other edge. And as you see, these are kind of protected from impurity scattering. So if I have an impurity somewhere here, it would not kind of bounce back, because the magnetic field defines just one direction of these localized orbits to move. So they're kind of like super highways where the electrons can move. So and it turns out that this integer n defined here is just the number of edge states. Okay? So now this is all good, and this was all found in experiments. So where did the topological insulator field start? Well, you notice that this experiment has a magnetic field on it. Then the magnetic field gives you the chirality of the edge states. It gives you the direction of propagation of the edge states. So the next question that I was asked is, can we get some sort of the same behavior, so a material with edge states, but without having and apply magnetic field on the system? And the answer is yes, and it's very easy to see why. So let's go back to our system of S and P orbitals that we had at the beginning. So my S and P orbitals now are defined by a 2 by 2 Hamiltonian. Say M is the on-site energy of the S orbitals, and P is the minus M is the on-site energy of the P orbitals. So they have different on-site energies. And of course, there's a coupling between them as I make the lattice constant small in this system. So as I make the lattice constant small in the system, there's a hopping between them. And the hopping between S and P, so P is an L equal 1 orbital. So the hopping between S and P has to pick up the slack of P equals of angular momentum 1. So it has to be some sort of K plus I, Kx plus IKY contribution. So this is in 2 dimensions. So this is kind of the Hamiltonian, the generic Hamiltonian of an S and P orbital system. And you notice immediately, especially, so this is something that the high energy people can relate. This is just the Dirac fermion. And you also notice that this Dirac fermion is fully gapped if M is non-zero. So if M, for any value of M equals non-zero, it's fully gapped. So now what I'm going to, but for M equals 0, it's gapless at Kx, at momentum Kx. So I'm choosing translational invariance. So momentum Kx equals Ky equals 0 is gapless. So now what I'm going to do is I'm going to make my space have this Hamiltonian everywhere, okay, with some mass M. Then nothing happens. I just fill my space with the Dirac particle. But now what I'm going to do is I'm going to create a domain wall in this mass where I'm going to flip the mass on half. For y negative, I'm going to flip the mass of the Hamiltonian. So I can clearly see that to go from negative to positive mass, you have to go through M equals 0. At M equals 0, that Hamiltonian is gapless. It's a bit more complicated than that because I've broken translational invariance in one direction, but the argument works. So you can clearly see that if I have a domain wall here in between M less than 0 and M greater than 0, has to go through M somewhere, the mass has to become 0, that Hamiltonian is gapless. And indeed, if you solve the system, you get a gapless edge mode flowing in one direction. And this edge mode has the following form. It's just exponential to the minus mass as a function of y. And you can kind of see that it decays away from the edge. It kind of like has like a decay property away from the edge. So this is, by the way, the same thing as Cullen-Harvey, Kaplan fermions in high energy physics. So now I'm going to build a sample of this material by just picking a material that has mass less than 0 in the bulk and in between in like a spatial amount, the size of whatever your sample you choose to be. And then I get 2 edge modes, one in one direction, one in the other direction. So the picture now is very similar to what I had before in the quantum Hall effect in terms of effective picture after I've taken away the magnetic field, etc. So basically, this Hamiltonian has the same physics that the magnetic field Hamiltonian, that the magnetic field system that I looked at before has. And of course, here the Hall conductance is just the number of edge states. So here the Hall conductance is 1, which basically comes from the fact that the Dirac Hamiltonian has a Hall conductance of 1/2 the sign of the mass. If the mass changes sign, 1/2 minus 1/2 is 1. And that's the Hall conductance. So the Hall conductance is just the number of edge states on one edge times the mass. So now I've told you that systems can have edge states, and I've showed you the simplest example of systems that can have edge states, which are, they can be bulk insulators, such as this one, and edge metals. So now where does extra symmetry come in? And the simplest way to see what symmetry adds is to consider now a one-dimensional chain. So I'm trying to give you kind of the hydrogen atoms of topological insulators. So a one-dimensional chain that I'm going to consider is the simplest example of a topological insulator that I can think of. And it goes like this. So I'm going to pick just sites on a 1D chain, and I'm going to call them A and B, but really they're the same sites so far. And I'm going to put a hopping in between them. And of course, if I put a hopping in between them, the dispersion relation E versus momentum, pick periodic boundary conditions now, so I have a momentum quantum number, it's just going to be 2t cosine of k. Just going to be something that looks like this. So it's a metal at half filling, or at any filling that's not 0 and 1. It's a metal. But now I'm going to kind of artificially pick a doubled unit cell. So I'm pick a doubled unit cell A and B. That means I'm halving my momentum. So I'm really just folding this side of the spectrum into this side, and the spectrum kind of looks like this, which is what I drew here. If it looks like this now, I'm going to turn on some dimerization. So now, as of now, the choice of the unit cell was just arbitrary. I could have chosen the other two as the unit cell. But now I'm going to turn on the dimerization between A and B sites. So I'm turning on dimerization. This opens a gap in this region here, you can see. So now at half filling, the system is an insulator. So I ask, what are its properties? Well, its properties are not really that interesting in the sense that if I draw the charge, so I can set a half filling and I can draw the charge distribution, and it's going to look something that's going to be some sort of an envelope function localized within the unit cell A and B for this type of dimerization. So I just drew it like this, translational invariant. But really, if I don't have any symmetry of the system, this charge distribution can move anywhere. So the system can have a charge distribution which, if I mess around with other dimerizations, if I add more hoppings, if I add more complexity to the system, it can move around. However, now, let me add inversion symmetry to the problem. And this is what, so I'm going to tell you what adding symmetry does. So let me add inversion symmetry to the problem. If you add inversion symmetry to the problem, that you immediately see that there's only two spots where this charge distributions can sit if you've got translational invariance and inverse symmetry. It can't sit anywhere in the lattice. It can only sit within a unit cell or in between unit cells. And in between unit cells corresponds to the other dimerization, where I dimerized in between the unit cells. Now, in between the first dimerization and the second dimerization, I have to go through the region where the system is a metal, so I've closed the gap and reopened it. So now symmetry has basically given me two distinct phases, and the distinct phases are given by the fact that the charge distribution sits within the same unit cell or in between unit cells. And actually, this is kind of like related to the issue of charge polarization, which was actually, this system was known since Zach, with the Technion, Zach's times, to have like a charge polarization difference between the two situations. So the more interesting thing now is that if I cut the system, so now I'm opening the boundary conditions. This was the periodic boundary conditions. I'm going to open the boundary conditions. I'm going to cut the system, and all these momentum states are going to just become discrete levels. But however, you can clearly see here that if I'm in what I define as the topological phase here, this really does no meaning because the unit cell is arbitrary, but I won't get into that. But the meaning is that there's two phases which are distinct, which symmetry tells me they're distinct. So if I cut the in between unit cells, then I've got a charge E over 2 on one edge and E over 2 on the other edge, which correspond to two mid-gap states here. So this is very different than the spectrum. This gap is this gap here, and the things, the charge E over 2 that remains on the end are those two states. One of them on one end with the other one on the other end. So now I can basically, with that adding symmetry, I have two different phases, but I can also think of topological, of going to higher dimensions and obtaining other kinds of topological insulators just by decompactifying this 1D chain. So for example, for 1D chain, I had that dispersion if I have an open boundary condition, and I'm going to create a bunch of 1D chains now to go to 2 dimensions. I'm going to make a cylinder of them and impose translation invariance in this direction, but in this direction I have open boundary conditions. And what you get is some dispersion. And if you started off with a trivial insulator here and the dispersion is not large enough, you end up being also trivial. But you can kind of see that if you started off at the beginning with my edge mode that I had on one edge, and from now on I'm just plotting edge modes on one of the edges, then I can get to this situation just by drawing things. I can get the edge mode to disperse, to connect at some other momentum now because I'm in 2 dimensions with a band, and to create a chiral mode. So now I've rediscovered my quantum Hall effect from the previous situation. So basically what I've tried to emphasize here is that the way to think about, you can think about topological insulators by just drawing pictures. You don't need to know any math, you can just draw pictures. So just pick a band structure, impose translational invariance in one direction, say, or in whatever direction you want, make one edge, and try to draw all the possible edge states you can get. So let's follow that argument, and let's now double the quantum Hall system. So now what I want to ask is, can you have a topological phase that doesn't have a time reversal breaking? And the answer is, of course, yes, because otherwise we wouldn't be here. And what you have, except that you need to introduce the concept of spin. So far I've talked about spinless electrons. Now I'm going to introduce the concept of spin. So if I have, and do kind of 2 quantum Hall effects, one for spin up with magnetic field up and one for spin down with magnetic field down. Each of these quantum Hall effects, as I showed you before, has one edge state, except now the spin up edge state is chiral and the spin down edge state is antichiral. So now I lead to this situation here. I get to this situation, which has an opposite, which has on one edge an opposite edge states going one in one direction, the other one in the other direction. So it's clear that if I talk about spin, of course this situation like this is not very experimentally realizable because I can't just get a magnetic field down for a spin down, but it's realizable with spin-orbit coupling, because spin-orbit coupling is effectively a magnetic field. You can understand it in that way. But the problem is with spin-orbit coupling, the spin is not a good quantum number. So talking about spin is not kosher, as it's appropriate to talk. Yeah. So the thing is, you can kind of relax the fact that you're talking about spin and just talk about time reversal. And let me show you how. So again, let's just draw edge states. So if I draw edge states, I'm going to take the system to be a cylinder with a momentum in this direction, and I'm going to, this is open boundary condition, so I have edges, and I'm just going to draw the edges on this, the situations that you can have on this edge. This is the bulk here, so I have a bulk, this is filled, don't worry about it. And I'm going to draw the possibilities that you can have in the bulk gap. So I want a metal in the bulk gap. So you can have this is boring, nothing happens. You can have this, the color code is this is spin down, this is spin up. You can have this, and this situation, in which you have two chiral edges of spin up and two anti-chiral edges of spin down, would be stable if you had spin conservation. Okay, so you can have two Landau levels of spin up, and two Landau levels would have two edge modes, and two Landau levels of anti-chiral of spin down on the same edge, and they have edge modes that go like this. However, if you break spin rotation symmetry, which spin-orbit coupling does, this situation would immediately open a gap here. Why? Because if all you ask, so I break spin rotation symmetry, but I still require time reversal. So all you have here is the time reversal partner of this point, because this is at k. Time reversal changes momentum is this point at minus k. So this situation, if I don't have spin rotational invariance, I can just open a gap. There's no constraint that will tell me that I have to keep this gap, because this spin color coding doesn't mean anything if I don't have spin rotation invariance. However, this situation is completely distinct, and this situation you can understand why it's distinct, because if they cross, if I draw a pair of edge states that cross the momentum 0, then this crossing is protected. Why is that? Well, I start by just thinking about this crossing as spin up and down, okay? So the spin up and down crossing, and then time reversal would protect this. But now I break spin up and down crossing. I break spin up and down, my spin up and down language, so I don't talk about spin anymore. But this crossing will still be protected, because time reversal will basically tell you that the state that was formerly spin up has to go in the state that was formerly spin down, although I don't talk about spin anymore. So this situation is stable to kind of like gapping and kind of like putting impurity bands. This situation is not stable. You can put an impurity band, and it will just, once you break spin rotational symmetry, it will break. So in this case, we know that you can draw a dispersion that has that form. So how do we find it? So all you can do is kind of shift it up and down. So how do we find it? Well, we go back to our nice S and P orbital system, and the way we find it is that, as I said before, in a lattice, so you don't want to apply a magnetic field up for spin up and a magnetic field down for spin down, but in a lattice what you can do is you can look at S up and P plus IP up orbitals and their counterparts with spin down, or time reversal invariance with spin down. So I need 4 orbitals per site to build what's a topological insulator. And then I'll have, so here I'm still assuming SD conservation, but I can break it by adding an off-diagonal term in this Hamiltonian. So I have a Hamiltonian which is for spin up, which is contained of these orbitals, and Hamiltonian for spin down, which is contained of these orbitals. And since they're S and P orbitals still, their off-diagonal terms are still kx minus iky and kx plus iky. There's still an angular momentum 1. So I'm back to the same Dirac Hamiltonian that I had before, just per spin species. Okay? So again, if I do this, if I do the same thing, if I do a domain wall in this mass in the on-site energy, so M is the on-site energy of S and P orbitals, M and minus M. I do a domain wall in this mass. So, by the way, notice that once I define this system, I define the spin up, time reversal fixes the spin down Hamiltonian. So once this mass reverses, this mass will also reverse, actually. So once I define the system, I can have just 2 edge modes on one edge that are protected from backscattering. And this is just that crossing that I drew before, this crossing. and this is the bulk. These are the modes. So this mode is the mode that moves in that direction. This mode is the one that moves in this direction. Okay. So the reason for this price is that actually such a system exists. And the way we got this idea is when, the way we got this idea is that we looked at all the semiconductors in the literature, and the semiconductors are kind of like of this type. So if you look at like gallium arsenide, it kind of has like a band structure of this type, where the S state, this is spin, it's got some spin, and the P states, these are spin 3/2 states. They're kind of like the S is above the P state. However, there's a series of materials called inverted materials, and these are inverted semiconductors. And in these inverted semiconductors, so this is kind of like gallium arsenide or like cadmium telluride. You see, notice a large concentration of cadmium here. So if you have mercury telluride, then what you find out is that somehow spin-orbit coupling brings this band down here. It brings it like this here. It opens gaps, hybridization here, and you're off with this situation where this band is S at k equals 0, S-like at k equals 0, and decays into like P-like here, because here it just came, there were just these bands. So this is called inverted band structure. And this immediately brings you to an experiment that you can propose. And you can kind of like make the situation very clear. So the experiment that you propose is the following. I put mercury telluride, if I put very little of this semiconductor in between two normal semiconductors, and I make a quantum well like this. The quantum well direction, well, the growth direction this is in this direction, but the quantum well. So if the thickness of the mercury telluride is small, then this whole system is going to behave not inverted. It's going to behave like cadmium telluride. If the thickness of mercury telluride is large, then this whole system is going to behave as mercury telluride. So now and that's inverted, and that's where the mass basically changes sign, and that's the topological insulator. So that's kind of like, so this inversion, I guess Yang will talk more about, but it's kind of a fundamental concept in topological insulators. So now you have two systems that you can play with. This is the trivial system. You just build two quantum wells, one with a large thickness, one with a small thickness. The one with a large thickness of mercury telluride acts non-trivially. The one with small thickness acts trivially. So then when you act trivially, these are the bulk modes of the bulk states of the quantum Hall effect, of the quantum spin Hall effect, which is the state I proposed before. That's well, these are the bulk modes of the quantum spin Hall effect. This is a trivial insulator. So, but these are basically bulk modes. So as you lower the Fermi level, because you can gauge these things, what you'll see here is electron conduction, Hall conductions, and nothing in between. Instead here, what you'll see is electron conduction, Hall conduction here, but in between, you'll see these channels of edge states, which will give you two terminal conductance of 2e squared over h. Why? Because there's two edge modes in each direction. So one edge mode here on one side, the other one on the other side of the sample. And if you drive the current in the other direction, you've got two edge modes in this other direction too. So just like we heard in the talks in the morning, is 2e squared over h. So this sample was built, and this is the result. So this result is basically telling you that what you've got is, if you build a thin sample, you've got large resistance, so low. So these parts are this is resistance. So this is 1 over this is conductance. So think of that as plotted exactly the opposite, to like inverse the plot. So this is low conductance, and this is the thin sample in the gap, almost 0, and large resistance, and this is a topological sample. And there's, in the eye of the beholder, for people who know this, if you didn't plot this on a logarithmic scale, this wouldn't look this good. But it's a prize, so it's a logarithmic scale. So this is really 2e squared over h up to factor of 3. But compared to this factor, it's good. Okay, so now, so that was the experiment that basically kind of convinced people at the beginning. Now Amir Yacobi has data that basically is very much the same on the same samples. That's the same like this. But really, what I wanted to show you, part of the new stuff, is that you can actually image these edge modes. So this is work that's done with Ali Yazdani at Princeton. That basically what he does is STM. So he just goes and tries to tunnel into regions of this quantum spin Hall state. And really, the quantum spin Hall state here is a double layer of bismuth, and you can see kind of like it sits on a substrate. And you can tunnel into these layers, and you can see the density of states of the edge state here, and here, and here, and here. There's a reason why it's actually angle dependent that I can tell you about. There's a reason why you don't see anything here. I can tell you about it in private, but basically what I want to show is that they've been imaged experimentally. So, so this is where I stop with the old stuff, and let me just try to give you 10 minutes of some newer stuff. And of course, everybody knows what happened. There's the 3D version of these materials, which is, by the way, not just a generalization of the 2D. I wanted to just point that out. It's profound. That Liang Fu and Xiao Liang are going to talk about. So basically, afterwards, topological insulators kind of inspired many directions that actually a lot of people in this room have worked on. So just try to find your name on these slides. It took a lot of time to write, so just try to read it. So basically, some of them that I'll point out, I'm involved in part of them, not all of them, but the ones that I mean, they're all very promising. There's a new direction, just finding other topological insulators with other symmetries, and we heard this morning some Floquet topological insulators, which I think will actually prove to be instrumental in finding topological insulators without time reversal symmetry, but with crystalline symmetries. Then there's a whole field of topological metals, Weyl fermions, and gapless Dirac fermions, which is basically kind of a spin-off of these topological insulating states in the bulk. You can find states which are metallic in the bulk, but the metals are protected. So kind of like the exact opposite of these states. You can look at Majorana fermions, para fermions, and topological superconductors, and I don't know, but I don't know if Liang would mention something about this, or Xiao Liang, and this is kind of like the A dagger is equal to A picture, and there's several interacting generalizations of topological insulators. One is an interacting generalization where the ground state manifold is still singly degenerate, but you've got symmetry protection on the edge, and you've got states which cannot be found in the single electron picture. And the other one is interacting topological insulators, where you kind of fractionally fill bands and you try to get states which have fractionalized excitation and ground state degeneracy. And there's of course a lot of work on
How many dimensions do you have?
yeah, so we're trying to talk. Yeah,
I think there should be a difference between, let's say, even an odd dimension.
there is.
Or properties of the Dirac equation.
So you're absolutely right. There's a difference between any. There's the difference already shows up at non-interacting level, and you'll have many differences at interacting level. So you're absolutely right. So people are trying to do it in all dimensions for non-interacting insulators with some symmetries. With these symmetries, time reversal particle Hall conjugation is this kind of a product of these two. This is sublattice symmetry. The classification is known in any dimensions with just these symmetries. But you can notice, so this is what I wanted to point out, this is the periodic table, and you can notice that the classification's been done, and the index, the number of states, this changes. So all we know from this table experimentally, all we've discovered are these two and this one. This is the quantum Hall, and these are 2D and 3D topological insulators. But notice that even with this table, you only have like these two symmetries, right? So then there's a bunch of missing dots here. So how do you get, so that means no topological class, means everything is adiabatical to each other. So how do you get classes there, and how do you get refinements of this table? Well, one of the things I wanted to point out, and that I find kind of fundamental, is that any symmetry will have its own topological class. So this is a table for these symmetries. If you add point group symmetry, which I think Liang will also talk about, you have different topological classes for different things. Now, the point of point group symmetry is there's 230 space group in 3 dimensions, so we've got our work cut out for the next 40 Sackler prizes. So so let me give you a flavor of what point group symmetry brings to the table. And I'm not going to be able to go through this very much. But point group symmetry can basically give you topological classes where you don't have any. And it can also give you topological classes that don't have, topological insulators don't have gapless edge states. So I've kind of like beaten down on the past that you must have gapless edge states. But it turns out that that's not true. Why? Because sometimes your adiabatic parameter, which was just the distance, kind of the adiabatic parameter was the distance between the topological non-trivial insulator and a topological insulator breaks the symmetry that stabilizes the state. So for example, if I had inversion symmetry, okay, or C4 or C2 symmetry, a system, and that symmetry define my topological class. If I had a surface that is this, if my inversion axis or rotation axis was this surface would break the symmetry. So that's not really an adiabatic parameter. So then you don't expect edge modes here. And one of the fundamental things that we found in the past, and by we I mean the royal we, everyone, found in the past years was that even though these topological insulators don't have gapless edge states or surface states in the energy spectrum, so topological insulators stabilized by some point group symmetry don't necessarily have gapless edge modes on all surfaces. So you can see kind of like a spectrum that's gapped. They necessarily have gapless edge states or surface states in another kind of spectrum, which is called the entanglement spectrum. And that's one thing that can characterize them. The other thing that we found that I want to go through is topological metals. So the other, this topological classification of point group symmetric topological insulators have given us a relationship between, say, Chern numbers or Hall conductances and a series of invariants. So for example, if I have inversion symmetry in 2 dimensions, I'll have inversion eigenvalues. And it turns out that you can prove that the product of the inversion eigenvalues at the 4 inversion symmetric points on lattice is -1 to the Chern number. So you can prove that, and Liang Fu will talk about the time reversal version of this, basically. The Chern number is just the Hall conductance. But now, let's say that the system has both inversion and mirror symmetry. What you know, if it's got mirror symmetry, is that a magnetic field or a Hall conductance is not compatible with mirror symmetry. And I can explain that to you, but basically you can think of it as having a mirror line. The magnetic field is an axial vector, so having a mirror line is not compatible with having a magnetic field, having a mirror line plane. So then, if you're in a system that has mirror symmetry and inversion eigenvalues, and the inversion eigenvalues have the property that their product is -1, so it would say that the Hall conductance is odd, but the system's got mirror symmetry, so the Hall conductance cannot be odd, then the system is a topological metal, by definition, can't be an insulator. So a lot of these things have been played, and there's topological metals, which basically means that as a spin-off of this point group symmetry analysis of topological insulators, we can now characterize systems which have in any dimensions protected gapless points. So graphene, for example, has protected gapless points that are protected by time reversal and inversion. So if you break either of them, you can gap them, but as long as you keep them, you can't gap them locally. Okay, so in the last 2 minutes, I want to show you something that you can get. I want to show you what you can get if you add interactions. So another new direction is basically the direction where you take one of these topological insulators, fractionally fill a band, and then turn on interactions. If you just fractionally fill the band without turning on interactions, the system would be a metal, just like a fractionally fill Landau level. The system would be a metal without interactions. But if you add interactions, then you can get fractional quantum Hall states. And these are, a lot of people in the audience have and are working on those. And these fractional quantum Hall states are very interesting because they have, as we heard this morning, fractional statistics and non-abelian statistics. And let me just show you a movie with non-abelian statistics. So this is kind of like a calculation done with some matrix product states, doesn't matter. But the point is the first time that you can actually do a calculation. So by the way, the calculations that were shown this morning with braiding was actually just the monodromy of the wave function. They didn't involve Berry phases. It's much harder to compute the Berry phase. The total braiding is the product of monodromy and Berry phases. So this calculation contains both of them. And this is for quasi-holes in a more Reed state. It's got 4 quasi-holes, which from what you heard this morning has just two degenerate states. So as I take one quasi-hole around another quasi-hole, I'm going to get not a phase, but a matrix. So this is called non-abelian. These are non-abelian anions, and they have certain properties. So what I want you to look is that this matrix, as I take this quasi-hole around this, it starts off, this is the braiding matrix. It starts off as diagonal, and look what happens. I mean, it's kind of poorly plotted, but look what happens as I go it starts picking up off-diagonal states, and after braiding, although I reach to the same configuration, I'll just get the matrix moving from identity to sigma x. And you can play this game, you can add it on topological insulators and get fractional topological insulator states that have ground state degeneracy here. So this is a spectrum that's got ground state degeneracy. This is one of these Chern insulators, one of these these Dirac Hamiltonians with a mass that changes sign, versus some momentum, and it's got ground state degeneracy, and this system will have fractionalized excitation. So let me just close by telling you in this fractional topological insulators, what I think is the next step. And I think the next step is finding a fractionalized state in 3 dimensions. So take a 3-dimensional topological insulator and fractionally fill it, and ask what kind of fractionalized state you get. In two-dimensional fractional topological insulators, we know what states you can get. In 3 dimensions, we don't know. So I'm going to leave the conclusions on the board and just thank everyone for bearing through this.